Hi guys, in this video we are going to discuss another interesting question which is from power factor. Before that we are going to do a detailed explanation in that theory, the significance of power factor. After that we are going to do a little small question regarding this one. Actually in the previous video we have already discussed about the power factor which is equal to cos 5, and we have discussed about the three types of power: active, reactive as well as apparent power. So we are going, if you haven't watched those videos, please watch that before watching this video, because it will give us brief understanding about the power factor introduction. So if you are new to this expert tutor channel, please don't forget to subscribe. Okay, without wasting our time, let's move to the question section. Okay, actually you can see that the active power does useful work on the load in terms of power dissipation, which simply means, actually we have already discussed about this one, active power, when we are considering about these two types of main power, one is active and the reactive, the apparent is the total or the mathematical sum of these two powers. When we are considering about the active power, we can directly tell the active power is the power we are going to use that, which simply means it's going to dissipate that energy. Let's say there is an electrical circuit or electrical instrument. The active power is the power we are going to get from that instrument, electrical instrument. So that's known as active power. When we are considering about the reactive power, actually we already discussed about this in the previous video. It's going to go back and forth, which simply means in an electrical circuit, if we have a capacitor or inductor, let's say a capacitor, when the current is going in a positive direction, it's going to store that energy. When it's going to, the current is going in the opposite direction, it's going to lose that energy, or it's going to return that energy to that circuit, which simply means it don't have a no net work. So it's not going to do a net work in that electrical circuit. So actually in the concept of significance of power factor, we can directly tell the active power is doing a useful work for us. It's going to dissipate that energy to us. In either terms, we can tell these two whether the active power is going to lose. Yes, it might have loss. The problem is we can't get that energy from that reactive power. It's going to store and dissipate, or store and going to return that energy to that electrical circuit. We can't get it from that. However, when you are considering about the resistor, it's going to dissipate that energy to us. So that's the meaning. So that's desirable that active power is closer to highest value as much as possible. So when we are considering about the active power, actually we have learned that equation Vi cos phi. To a certain voltage and current, we can tell when the cos phi, the power factor, is near to 1, it's going to have the maximum value. So it's always better to have the cos phi tends to 1. So that's the main idea. So we are going to have a higher cos phi. The first reason is that, let's say there's an inductive load, which simply means the cos phi is going to be lesser, because when there is an inductive load, actually we have learned that the phi, the phase angle, would be higher, which simply shows that the cos phi would be lower. So if there is a power factor, increased power factor of an inductive load, we should add a capacitor in parallel. So some might have doubt whether why can't we add the capacitor in series? Yes, you can add it, but there's a little bit problem. So we are going to discuss that in a few minutes later. But this term, though, this process is known as power factor correction. So you need to know this term, power factor correction, which simply means to increase the power factor of an inductive load, you need to add the capacitor in parallel. So you need to know that. So in other terms, what are the demerits of that power factor or lower power factor? When you are considering about the total power, the active power we are going to get from that source, which is known as P is equal to Vi cos phi. If you subject that I, you can directly get an equation of P over V cos phi. Actually, we can get that if that's the constant voltage we are providing and a power we are going to supply to that circuit. If there is a cos phi, the increase in cos phi, we can tell the I is going to be lower. In other terms, if the cos phi is lower, which means the power factor is lower, the I is going to be higher, which simply means the current drawn from that source is going to increase. What's mean by that? When the current is increasing, we can tell what's the demerits of that. Actually, when the current increases, we knew that there are two main problems. The power loss in the distribution I squared R, the equation would be I squared R, when for a certain resistor in that line, the line loss in that distribution would increase to that square I squared R. So we need to control that I. So we need to have a higher cos phi or higher power factor. Likewise, when you are considering about the first part needs thicker wires, yes, you also need that. The reason is to lower this power loss in the distribution. Actually, if you can't control this I, we need to reduce this R, which simply means we are going to have a thicker wires. When the area, the cross-section area of the line increases, the resistor of that line is going to decrease. So when you are considering about that process to increase that cross-section area, we are going to spend a lot of money to buy or to use lines for that second instance. So the problem is, the best solution is we are going either these two are the main demerits, so we are going to increase that cos phi so that we can drain this current, or the drawn current from that source would be decreased, would be beneficial for us. So in the next point we are going to go to the same point. These are the main theory brief of these significance of the power factor. So actually the main brief thing is we need to have a higher power factor. So in this case, when we are considering the power factor correction, we have told that capacitor, when there is an inductive load, we are going to add the capacitor added in parallel. Why we need to add in parallel? Actually, if there is an inductive load, we can add it in a series too. We can add a capacitor in series too. It's going to reduce that. Let's say there is a phasor diagram, so it would be easier if you use a phasor diagram. Let's say there is a phasor like this. When we are considering about a series diagram, there, let's say this is I, the I is going to be, when we are considering about the series, we can tell the I is going to be the reference line. So let's say there is a voltage, this is the main voltage of that, this is V of that certain element, this is phi. Let's say this is the certain instant. So when we are considering about this, when we add another element, the I is not going to change, so that we are going to, the I is going to be changed, however the voltage also is going to be changed for that certain element. So in certain things, let's say there we are going to add another inductive, let's say in this side, another capacity. So here I have drawn inductive circuit load, and we are considering about to add another capacitor in terms of this thing. So it's going to be like this. It's going to show in a negative direction, because that I is in the reference line. We can directly tell the voltage would be in that downwards direction of Y, so that we can tell that if the voltage goes this one, let's say this is V1 and V2, it's going to change over here, so the voltage might drop. Yes, that's correct. Oh, the phase angle, if we took a lower V2, let's say this is the V2, let's say this is the V2, the voltage V1 is going to drop in that certain element. So it's likable, so it can happen. How the problem is whether we can attain this. When we are considering about the circuit element, the element would require a certain voltage. When we are considering about some home appliances, we are going to have that in a 230 voltage. So we can't change this voltage for that certain element. But what can we do is we can change that current. That's why we are going to do this capacitor. We are going to add that in a parallel, because if we add these two in a parallel, the voltage is not going to be changed in that certain element. So we can draw a phasor like this. The voltage is not going to be changed. If we are consider about the inductive circuit, we can tell if there is an inductive load, the I would be in this direction. Let's say this is I and this is phi. So this like this. This is the first element, circuit load, which is inductive. Likewise, we can draw that. When we are considering about adding a capacitor added in parallel, the I is going to be changed. But the question over here is, if we add another capacitor in parallel, the I, let's say the new I would be like this. So if you consider about this thing, the I is going to be changed. That's okay. But the thing over here is the phi is going to be decreased, but the total voltage across that circuit element is not going to be changed if we are adding in parallel. So that's why we are going to add that capacitor in parallel. Otherwise we can also add it in the series, but the thing is we can't change that voltage. It won't work properly if we change the voltage, but we can adjust that current little bit. We can have a range of current. So that's the main thing. You can't change this voltage. You should have a minimum range of voltage, so it's better to have the same voltage over here. So that's the main reason. So you need to know that to increase the power factor of an inductive load, we are going to add that capacitor in parallel. So let's look at the question, so it would be very easy to understand. Actually, they have given there are three impedances, which is 70.7 plus j, like that. They are in the parallel. So the first question is they are asking about the total admittance. We have already discussed these types of questions, so I'm not going to waste the time. So I'm going to directly calculate that. When there's a parallel, we can tell it's going to be 1z. 1 over z would be 1 over z1 plus 1 over z2 plus 1 over z. Actually, we knew the value, so we can directly substitute that. So here I'm going to use this one. So this is y. I'm going to use the calculator over here. Actually, we have already done a video how to use the calculator, Casio 991EX calculator, to find or to solve the complex number Cartesian forms as well as the polar form. So if you haven't watched that, please watch that before doing these sums. So I'm going to do a little bit faster. So let's change this one. We need to check whether it's in the complex number form. Yes, it's in the complex number form. Yes, that's correct. Okay, let's move to the question. So the first part is 1 over z1. So I'm going to use 1 divided by the z1. We actually knew the value, 70.7 plus I into 70.7 plus another one, this one, 120 divided by, sorry, I need to use the bracket. Sorry, I don't need 1 divided by 120 plus 160 into I. Okay, that's finished. The last part, 1 divided by, in bracket, 120 plus I into 90. Yes, so we can double check it again. I think these values are correct over here. Yes, let's see if the correct answer with the answer would be this one. So this is going to be the admittance, 0.0154 minus 0.0151 j. Okay, this is the admittance. You can write it like omega minus 1. So that's the question for the answer for the first question. But they are asking about the current. However, I'm not going to do that. Whether we need that. Actually, we knew the voltage, so we can directly find that. So let's try that too. So please pause the video and try to do it in your own, otherwise it won't be useful for you. So if you are considering about these two polar form, it would be very much easy to solve when we are considering about the current. So if you change that, you can use the calculator, but I have already done this question, so I have the answer with me. So I am going to write it 215 with the angle of minus 44.3. Likewise, from that we can tell that the current would be equals to V over Z, which simply means V into Y, the admittance. So when we are considering about that, if we multiply these two values, 250 with the angle of 0 into 0.0215 with the angle of minus 44.3, is going to return the value of 5.37 with the angle of 44.3. So this is the main thing. If we draw a phasor for this type of diagram, they are in the parallel. So I'm going to consider a certain circuit, that element which is having these three impedances in a parallel. Let's say this is voltage as a reference. If we draw the voltage as a reference, as the polar is 0, polar angle is 0, phase angle, the I would be in this direction. Actually, we knew that the I is having minus 44.3. So now we have finished one part. So the question is, we are going to add a pure reactance, consider that point, pure reactance, that will bring the power factor unity when connected across the supply. So in this question, we can't change the voltage as that certain, for that certain instrument, we are going to supply the same voltage. The thing we can do is, we are going to, as you can see over here, the voltage is leading, so that it's going to be an inductive circuit. So for that we are going to change it for capacitor, or we are going to add a pure capacitor, because when we are considering about the pure reactance, we can't add the inductor. If we add another inductor, the inductance circuit or the inductive of this circuit is going to be increased. So actually we can do that, we can add the capacitor in the parallel. So the question is, how much that reactance would be, the pure reactance, what's the value of that pure reactance? Usually you can easily figure it out. Let's say this is the total admittance we are having. So when we are considering about the admittance, the question here is, we are going to make this admittance to the real part only. Actually we are having another part called, what's that, this is the complex number part, J 0.0151J. So to cancel out this part, we are going to add plus 0.0151J, so that we can tell the admittance is going to have only real part. What's the benefit of this? When we are considering about the reactance, if we make this angle 0, actually we can tell the I and V, the cos phi would be 1. So that's the question they are asking. Pure reactance that will bring the power factor unity. Unity means the number 1. When we are considering about the cos phi to be the cos phi to 1, we can tell we need to add this part, so that admittance is going to have that phase angle of 0. So the current is going to have the same phase angle 0. So the cos phi would be 1. So we need to add this part in our parallel. So actually we knew that this is one parallel circuit. So the first parallel circuit's admittance. When we are considering about another parallel circuit admittance, we can tell we are going to add these two admittance, or in other terms we can tell, let's say this is the resultant of first one, that R1 plus 1 over Z2. This is known as 1 over Z equivalent. So we are going to add them in parallel, so you can directly add them. So this is going to be the 1 over Z2 value. So if you change that, you can directly get the Z2 value over here. So that would be the answer. The pure reactance, actually they are asking about the reactance, so you need to add up on that, or you need to inverse that. So you are going to get that value. So the 0.0151 is 1 over Z2. When you are considering about the Z2, it's going to be 1 over 0.0151. So this is known as 1 over Z2 is known as, this part is known as susceptance. So you need to know that term too, that this part is known as susceptance. And when we are considering about this one, likewise we are going to call this part as conductance. So you need to know that real part, the real part is known as conductance. In an admittance part, the real part is known as conductance, and the imaginary part is known as susceptance. Likewise, when you are considering about the Z, the impedance, the real part is known as resistance, and the imaginary part, the real number before that imaginary part, this part is known as reactance. So you need to know these four terms, because they might give that terms and give the value and ask to find or ask to sort that out. So after that they are asking about the total current. Actually we knew that there would be a change in that total current, because we are going to add another few items in the parallel, so it's going to change that total admittance. So there will be a current, a change of total current. So you can do that and try it in your own, and if you can, please sort it out and give the answer in the comment section, so I can also watch that and other students also can watch that. Thank you for watching. See you in another video.